Earlier, I referred to an easy way and a hard way of calculating electric field. I said the easy way was doing the force divided by the charge, and that's certainly true. But what if you had a problem where you didn't know the force? So this is a brand new problem. I've got two source charges, Q1 and Q2. I'd like to find the electric field at point P. I don't have a charge at point P, and I never calculated the force at point P. And I would like to calculate the electric field. So what I'm going to have to do is use my expression for finding the electric field around a point charge. I have 2 point charges, so I'll have two expressions, and I'll have to do a vector addition. So let's write down the steps for doing this problem, just like we wrote down the steps for calculating forces. So the first step we do is we draw electric field vector 1 and electric field vector 2. And it's important to draw those at point P. I'll go on in a minute to show you how not to do it. Second step of the problem is find the magnitudes of those electric fields. Step 3, the electric fields are vectors, so find the components. And our last step is do a vector sum. It can be easy to get a little bit tangled when you're doing these kinds of problems, but if you follow these steps, you'll never go astray. So if you always do the problems in these orders, step 1, 2, 3, and 4, you're never going to get your problem wrong. So I encourage you to follow these steps. So we're going to do step 1 first, which is to draw electric field vectors E1, so the electric field vector due to charge 1, and the electric field vector due to charge 2. I would like for you to hit pause here, grab a scrap of paper, and you draw the electric field vectors first. I want to head this off the pass if you're not quite sure how to draw them correctly. So on the next slides, I'll show you how not to draw it, and then the slide after that, I'll show you how it does have to be drawn. So when it comes to drawing our electric field vectors, we know that if our source charge is positive, the electric field points away from the positive charge, and if our source charge is negative, the electric field points toward the source charge. Okay, so in our picture, Q1 is a positive charge. The electric field has to point away. Let's draw a vector that will not accurately represent the electric field at point P. So if you draw and write E1 here, this will get you 0 points on an assignment and a test. Likewise, for Q2, if you draw your electric field vector like this will not get you any assignments, any points on an assignment. So if you draw your electric field vectors like this, these will be marked wrong. When you draw the electric field vectors, you have to draw them at point P. Okay, let's go through one more way that you should also not draw your electric field vectors. The second way not to draw them would be to draw your electric field vectors with the arrowheads at point P. So if you draw E1 here and E2 here, this is also considered wrong. Okay. So you can't put the arrows at point P. To draw it correct, you must have the tails at point P and they have to be drawn on point P, not anywhere else. So you take your pencil, you put it right on top of point P, and then you go the way you have to go. Let's draw them correctly on the next slide. So step 1 of our process is draw E1 and E2. So for E1, we put our pen on top of point P and we go away from our positive charge. There's electric field vector E1. For electric vector E2, we put our pen on top of point P and we go towards charge 2. So there's E1 and E2. E1 goes away from it, E2 goes towards it. Our next step will be to find the magnitudes of E1 and E2. Our next step is to find the magnitudes of electric fields 1 and 2. The magnitude of electric field 1 is Coulomb's constant K times the magnitude of charge 1 divided by the distance r1 squared. r1 refers to the distance between our point and our charge 1. That's given as 1 millimeter in our picture. 8.99 times 10 to the 9 newtons meters squared over coulombs squared. The magnitude of the charge is 1 nanocoulomb, so that's 1 times 10 to the minus 9 coulombs. Notice we use the magnitude here, divided by the distance squared. 1 millimeter is 1 times 10 to the minus 3 meters. That's got to be squared. So the magnitude of our first electric field is 8.99 times 10 to the 6 newtons per coulomb. Okay, next we have to find the magnitude of electric field 2. The magnitude of E2 is K times the magnitude of charge 2 divided by R2 squared. R2 is our distance, do that in a different color, from P to our charge. So there's R2. We've got to find R2 using Pythagorean theorem. We see that R2 is the hypotenuse of a right-angled triangle where one leg is 2 millimeters long and the other leg is 1 millimeter long. So R2 is going to be the square root of 2 millimeters squared plus 1 millimeter squared. So then R2 is equal to 2.24 millimeters. Let's put this in our equation for E2. 8.99 times 10 to the 9 newtons meters squared over coulombs squared times the magnitude of charge Q2, 1 times 10 to the minus 9 coulombs, divided by R2 squared, 2.24 times 10 to the minus 3 meters squared, gives us a magnitude for our electric field E2, 1.80 times 10 to the 6 newtons per coulomb. It's smaller than E1, but that makes sense because charge Q2 is further away. Okay, there's step 2 done. Our next step in the problem now is to find the components of E1 and E2. Our vector E1 points straight up. Since it doesn't point left or right, the x component would be 0. So E1x equals 0. The y component, since it points up, our y component is going to be positive, and it's going to be the whole thing because all of the vector points straight up. 8.99 times 10 to the 6 newtons per coulomb. Okay, there's E1. That one's pretty straightforward. What about E2? Well, E2 has x and y components. The x component points to the right. Let's get our coordinate system in here. Positive x right, positive y up. So there's E2x, and our E2y points straight down. That means if we're going to find x and y, we're going to need to figure out that angle in right there. Let's call that angle theta. And then because what I learned of as the Z theorem, I don't know if that's really a thing, our angle theta here is the same as our angle theta here. It's because we've got two horizontal lines there. So we'd like to find our angle theta. We remember that tan theta is opposite over adjacent. So the opposite is 1 millimeter, the adjacent is 2 millimeters, so tan theta is 1 millimeter divided by 2 millimeters. So then theta is the inverse tan of 1 over 2. Inverse tan of 1 over 2 is 26.6 degrees. Okay, back to our E2 vector. E2x is positive because it points right. It's adjacent to the angle, so we're going to use cosine. So E2 times cosine 26.6 degrees. We'll plug in that E2 was equal to 1.80 times 10 to the 6 newtons per coulomb. Multiply that by cosine 26.6 degrees. And what we get for the x component of our vector E2 is 1.61 times 10 to the 6 newtons per coulomb. There's our x component. If we look at our y component, we see that the y component points down and it's opposite our angle theta. So for our y component, e2y, it's negative e2 times sine 26.6. So minus 1.80 times 10 to the 6 times sine 26.6 gives us a y component of negative 0.805 times 10 to the 6 newtons per coulomb. Okay, now we've got the components. Our very last step to find our total electric field is to do our vector addition. Our last step now to find the total electric field is our vector sum. So since the vector sum is the sum of vectors e1 and e2, means the total x component is e1x plus e2x, and our total y component, ey, is e1y plus e2y. Okay, so our x component then, ex, is equal to 0, that's e1x, plus 1.61 times 10 to the 6 newtons per coulomb. That gives us 1.61 times 10 to the 6 newtons per coulomb. Okay, let's do our y components next. Our ey is e1y, that's 8.99 times 10 to the 6 newtons per coulomb, plus e2y, that's minus 0.805 times 10 to the 6. I got to squeeze in my newtons per coulomb there. And that gives us 8.19, sticking with the 3 sig figs, times 10 to the 6 newtons per coulomb. Okay, now we finish by writing our electric field as a vector. E equals our x component, 1.61 times 10 to the 6 newtons per coulomb I, and our y component, 8.19 times 10 to the 6 newtons per coulomb J. So there's our final answer. That's our total electric field, which is made by the two source charges, Q1 and Q2. Notice there was never a charge at point P, and we didn't need a charge there to find our electric field. Next, let's move on to point B. So part A of this problem, we found the electric field at point P. Part B, and heads up, this is often part P, what would be the force if we plopped a little electron right there at point P? Well, there's kind of two ways to do this. There would be a long way or a harder way. For the long way, we would put our proton right here. We might call it charge Q3. We would have Q1 right here, and we would have Q2 right here. In this method, we would draw the force between 1 and 3 and the force between 2 and 3. We would find the magnitudes. We would find the components, and we would do a vector sum. That would work out just fine. You would get the correct answer, but it would probably take a while. There is a short way, and the short way is to remember the relationship between electric field and electric force. The force on an object Q placed in an electric field is the product between those two things. So Q is the charge that we place in our electric field. That's a proton. You include the sign of the charge here. That's plus the fundamental charge. And we're just going to multiply it by the electric field found in part A. Okay, we'll multiply through using our distributive property there. We get 2.58 times 10 to the minus 13 newtons in the x direction, and 13.1 times 10 to the minus 13 newtons in the j direction. So that's a real quick way to find the force if you already know the electric field. For some extra practice, you can go back to our problem with the 4 charges and find the electric field at the center of the square using a vector addition. And you can go back to our triangle and find the electric field at the top of the triangle using a vector addition. Doing this as practice should make sure you're really comfortable with that kind of vector manipulation.